Gaia and TESS unveil a remarkable diversity of young clusters in the solar neighborhood. Hi, my name is Jason Curtis, and I'm an Associate Research Scientist at Columbia University. I also work with a Science Research Mentoring Program at the American Museum of Natural History. This program matches researchers with local high school students, and together we conduct research during the school year. I'll share some of their exciting work later on in this presentation. Over the last few years, Gaia has transformed our view of the Milky Way, particularly of the substructure within it. With Gaia DR2, we finally had access to high-precision proper motions and parallaxes for over 1 billion stars, radial velocities for 7 million stars. And with these data, all kinds of different structures have been identified. New stellar streams, known clusters now have giant halos and extended tails, a wide variety. The question is, are these structures being found in Gaia actually composed of stars that were born together and share a common age? To answer this, TESS is critical. That's because TESS is surveying the majority of the sky, recording full-frame images every 30 minutes, sector by sector. With these data, we can extract light curves and measure rotation periods, and it's the rotation period that's key. This is because benchmark star clusters have taught us that we can tell time with spinning stars. If you take a collection of stars born together and plot their masses versus how fast they spin, the stars organize themselves into tight sequences. For example, the Pleiades, at 120 million years, shown in blue, has a prominent slowly rotating sequence, rapid sequence, and for masses less than 80% of the Sun, there's a fanning out toward rapid rotation. Over time, these rapid and slow stars merge together as they all spin down, moving upward in this diagram. And so by the age of Praesepe, 670 million years, most of the stars congregate along one sequence, down until about 0.3 times the mass of the Sun. You see this kind of waterfall effect falling towards rapid rotation. The point is, clusters of different ages have unique mass versus rotation period distributions. And so it doesn't really matter what's going on with gyrochronology and our attempts and failures to model it. What is key is that a group of stars that share a common age have a unique signature in this diagram. And we can compare, first of all, we can use this to assess whether stars actually do share a common age. And two, we can compare a cluster or a group of stars rotation period distribution to benchmark clusters that are well characterized to determine their age without really requiring an actual model. At the start of 2019, Stefan Meingast published an exciting study where they looked at the velocity substructure in the solar neighborhood. There was a little clump in velocity space of 256 stars that, when they plotted the 3D positions, turned out to be an extended stream 400 parsecs long, wrapping around 1/3 of the sky, and they concluded it was 1 billion years old. I actually learned about this on Twitter when Jason Wright, who advised my PhD work, tagged me in a post where he was really excited to learn about another old group of stars near the Sun. Now, when I ended up measuring the rotation rates for these stars, the rotation period distribution matched that for the Pleiades, showing it's actually only 120 million years old. But it's still amazing nonetheless. Subsequent membership searches actually showed that the population size of this stream rivals or even surpasses the Pleiades. There's somewhere between 1,300 and 2,000 stars in this stream, and it's 700 parsecs long. Within the stream, you can see in these XYZ plots on the left, there's actually substructure. There's different overdensities along the stream. Keith Hawkins followed up with spectroscopy using archival Lemos data and their own spectra collected at McDonald Observatory. And one of the things they looked at was the lithium abundance as a function of effective temperature. Now, this diagram is similar in principle to a color magnitude diagram, or to the rotation period distributions we were looking at before. A coeval population of stars will have a unique signature in this diagram, and you can see the Pleiades in red is distinct from the Hyades in purple, which is distinct from the galactic field stars, which are typically very old, billions of years old, compared to these young clusters. And the measurements of lithium for the stream overlap the measurements for the Pleiades, supporting our conclusion from gyro chronology that they do in fact share a common age. One of the amazing things about TESS is that it simply collects data and puts them on the internet. And it does this in full-frame images, so we don't have to do careful target selection beforehand. We don't really have to know what's interesting before the mission conducts the survey. And in fact, the stream was discovered after TESS had already looked at it. So if we had to pick and choose carefully beforehand, we would never have these data. In fact, one star was already recognized to be a TOI when we realized that this stream was young. TOI 451. Elizabeth Newton realized this and organized this fantastic group of people to thoroughly characterize this multi-planet system. This is really important because the K2 survey of the Pleiades turned up no planets, and so this is the first Pleiades-aged planetary system in a young cluster. What does Gaia teach us about open clusters? These are denser, gravitationally bound objects, much different from the stream. This study looked at 10 young nearby star clusters. Here you see them edge on and top down in the galaxy, and the membership list currently shown is from Tristan Cantat-Gaudin's membership survey in 2018. They focused on the immediate vicinity around these star clusters, and that impacted the membership that was derived. These are very compact, 10 or 20 parsecs in size, really reflects the classic understanding of a star cluster. But when Stefan Meingast broadened the search, looking for co-moving stars in a larger volume of space, they found extended halos, tidal tails, well, really what they call corona, surrounding each of these star clusters. Stars that appear co-moving and appear to share a common age based on the CMD, but which are hundreds of parsecs away from the core. Marina Kunkel and Kevin Covey separately performed an unsupervised clustering search for structures in the nearest 1 kiloparsec, and they found a variety of substructure in the galaxy. And here, Meingast is showing their membership list for the 10 clusters. And you can see these are bigger, messier, more scatter. The question is, which of these views accurately reflects the membership of these star clusters? Do star clusters really have members extending out hundreds of parsecs into space? Luke Bauma studied the NGC 2516 cluster. It's the purple one at the left. In a recent paper, and what Luke did, and he'll talk about this on Thursday in the Planets Around Young Stars Splinter session, he used rotation periods from TESS and lithium abundances from Gaia ESO and Galah to determine which stars in this extended halo share a common age with the stars in the inner core. And what he found really is amazing, that there are coeval stars that are co-moving at 500 parsecs across, much bigger than the 10 parsec classic tidal radius. In a 2019 study cleverly titled Untangling the Galaxy, Marina Kunkel and Kevin Covey used Gaia Astrometry combined with an unsupervised clustering algorithm called HDB scan to detect structures within the nearest kiloparsec. They actually found 1,640 unique structures containing 288,000 stars. You can see at the left the top-down view, lots of groups, along with what they call stellar strings, which are elongated filaments, perhaps analogous to the stream we talked about before. In the bottom panel, you can see the distribution of sources in their Theia catalog in blue, and the known open clusters analyzed by Tristan Cantat-Gaudin in yellow. And you can see that these Theia groups really are all over the sky and contain large numbers of stars. And what we want to know is, are these actually composed of stars that share a common age that were actually born together? Are these streams and strings and structures real? Well, let's look at a few of them. First up is Theia 456. Theia 456 is being studied by Jeff Andrews. Jeff noticed that 84 of its stars were already observed by LAMOST. This means that we can study the spectroscopic metallicity of its stars. Here you see the right ascension versus declination. It's really surprising to see this thing, wrapping 25 degrees around the sky. And you can see color-coded the metallicities measured from LAMOST. The inset shows the histogram, the blue bars, of the Theia 456 members, and the orange histogram shows the expected distribution from field stars. So this shows that the stars in Theia 456 share a common metallicity. But that doesn't necessarily tell us if they have the same age. So we measure rotation with TESS, of course. But one of the troubles with rotation is that normally we plot it against photometric color. And Theia 456 being so big across the sky and fairly far away, it's I think 500 parsecs, is that there's a high degree of interstellar reddening and variability in the reddening across the stream. So when you plot the color period diagram at the left and compare it to the Pleiades and Praesepe, the first thing we notice, and these are the blue points, is that there is a slow sequence. So it shows that a lot of these stars share a common age. But what's trickier is the comparison with the benchmark star clusters, because the reddening correction is a little complicated. First of all, the differential reddening kind of smears things out. And second, the absolute reddening value is a bit uncertain. So fortunately, we have the spectroscopic temperatures from LAMOST for the Pleiades and for Theia 456. And that's what we compare against the rotation periods at the right. The spectroscopic temperatures are insensitive to interstellar reddening, and they show that the distributions overlap precisely. So we conclude once again that this unique stream also is similarly aged as the Pleiades. Speaking of the Pleiades, what has Gaia shown us about its structure? Jonathan Gagne, a few weeks ago, published a study that looked at some of the young nearby moving groups, clusters, and these new Theia groups. You can see in the top right the X versus Y top-down galactic coordinates. You can see the Pleiades in blue. Actually, the Pleiades is in black. And surrounding it in blue is a giant halo identified by Marina Kunkel as Theia 369. The gray points are the AB Doradus moving group. And then the yellow, red, and purple are different Theia groups, which are in this general vicinity of the Pleiades. They appear young, like the Pleiades in their color magnitude diagrams, and they share common velocities as the Pleiades, as you can see below. So the question is, are these related somehow? And they speculate that perhaps that red blob of stars is a trailing tail, tidal tail behind the Pleiades. Perhaps AB Doradus is also consists of stars that were once part of the Pleiades cluster. The first thing we should do is test if the stars in these different pockets are actually 120 million years old. So we measure rotation once again. We have an excellent rotation period catalog for the Pleiades from Luisa Riebel's 2016 study using K2 data. You can see that they map out the slow sequence, the rapid sequence, the fanning out at lower masses. So let's compare it to the AB Doradus moving group. This is work completed by Lisette Gonzalez. She has a poster which you should see, and please talk to her during the poster session. And you can see that her rotation period measurements for AB Doradus perfectly overlap the Pleiades distribution, so it shows that they share a common age. How about Theia 301, the red blob? Once again, the rotation periods from TESS confirm that it has an age similar to that of the Pleiades and also now AB Doradus. So these various apparently distinct structures in physical space share a common motion and a common age with the Pleiades. But that doesn't mean these stars necessarily were born in the Pleiades and then left. what if these are signs of a larger star formation complex, which the Pleiades would be a part of? I'd like to remind you of the Orion complex and the Skocin-Ob association. These are sites of active star formation or recent star formation, and you can see there's lots of substructure in these regions. And these regions are just, spread out by 100 parsecs. So I think one of the open questions, well, what these Theia groups are they the remnants of open clusters that have been tidally dispersed, or did they start out more decentralized like Skocin-Ob association? What would these different cores in Orion look like in 50 million years, 100 million years? Next on the list is Theia 520, home to Kepler 52 and Kepler 968. So I was working on finding clusters and new Theia groups that have ages somewhere between the Pleiades at 120 million years and Praesepe at about 700 million years. We want to fill in the gap and study how the rotation rates of these stars change over time. How do the slow sequences form? When do they spin down? And so I stumbled across Theia 520, and I noticed that its coordinates were actually fairly close to the Kepler field. And when I cross-matched the list of candidate members, I realized that Kepler 52 and Kepler 968 were among them. You can see at right the color magnitude diagram suggests the stars actually are related because it's tight. But the problem is the upper main sequence, where the age information is encoded, is too sparse. Is it 100 million years old, 250 million years old, 430 million years old? There's ambiguity because there's not a clearly defined main sequence turnoff. So once again, we appeal to gyrochronology. Now this time, because the cluster is somewhat older, TESS can't do everything for us. Now, one of the amazing facts about Theia 520 is that a portion, the southern portion, was in the original Kepler field, and the northern portion is actually in the TESS Northern Continuous Viewing Zone. So we have TESS data, Kepler data, and we also have Zwicky Transient Facility ground-based light curves. And you can see examples of each for Kepler 968 at the right. And this shows a different quality, different character of the data. TESS, a single TESS sector, is rather short compared to the longer observing baselines provided by ZTF and especially Kepler, of which we're only showing 8% of the available data here. The Kepler data quality are simply unparalleled, but we only have data for 10 stars. And ZTF, much coarser, right? Observing nightly since March of 2018, it's a sparser light curve compared to TESS or Kepler. But with a longer observing season, we still can recover rotation rates. And so for this star, we actually can recover exactly the same rotation period from these very different kinds of light curves. And I should say for this, ZTF provides archival light curves. An example is shown at the top panel here. But they also provide archival imaging data. And that's actually what I use. So I download cutouts from the archival imaging, and then I re-extract the photometry for the target and also some neighboring reference stars. And then I calibrate the light curve and find that we can dramatically improve the photometric precision in many cases. As you can see here, the rotation period for this example star is clearly evident in the light curve that I've produced compared to the archival light curve. So what do we see for Theia 520? Well, at the left, we see the Kepler data. In the middle, TESS, and at the right, ZTF. Each of them give a consistent picture. But what's important is that TESS overwhelmingly provides the rotation periods that show that Theia 520 is composed of coeval stars. Kepler, we can get the age for the cluster, but we only have 10 measurements. So I think it would still be uncertain if the group overall actually was composed of coeval stars. Now you can see why TESS and ZTF complement each other in the right panels. ZTF can reach longer rotation periods. Now here, because of the age of the cluster, we're only getting up to 15 days, but we can actually recover rotation periods with ZTF up to 100 days. And ZTF also can reach somewhat fainter magnitudes with TESS. And so in this case, we can reach lower mass stars. The red symbols here are actually Kepler 52 and Kepler 968, and you can see them falling on the slowly rotating sequence for this grouping of stars. So this proves that Theia 520, the tightness of this slowly rotating sequence, proves that Theia 520 is truly composed of coeval stars. And when we compare it to other benchmark star clusters, some of which are shown in this plot, we can infer an age of 350 million years. Basically, instead of appealing to this or that gyrochronology model, we just compare it directly to other star clusters. And we can basically, it's older than Pleiades, obviously. It's younger than Praesepe, obviously. But we have lots of other clusters in the intervening gap now. And so we can really sandwich it in at 350 million years. This finding is important because there are not actually that many young cluster planets known. And these 6 planets, 52 and 968, each have 3 validated and confirmed planets, confirmed via transit timing variations. And so we can immediately add these planets to the young cluster sample without needing to go through the extensive validation process because it's already been done. A lot of the TESS rotation periods I've talked about so far for the neighboring Pleiades groups, Avidoratus and that Theia 301 group, for the Theia 520 group, home to Kepler's 52 and 968, for Kepler 456, that really long thing on the sky. These are all produced with an interactive tool built by my high school students during the 2019-2020 school year. Here you can see us happily working away at the museum on February 5th, just weeks before the museum was shut down during the pandemic. When this happened, like everyone else around the world, we were forced to work remotely. We had to figure out how to cope with that. One thing we decided to do was to migrate our Python code to the online environment provided by Google Colab. So this works in your Google Drive account, and they provide a Jupyter Notebook environment from which you can run your Python commands. And so we built this interactive tool that allows you to change the different light curve calibrations, what sectors you're looking at, interact with the data in different kinds of ways, and then classify and validate the rotation period measurements. And this has really made our life a lot easier because we can involve newcomers to research. We don't have to worry about their hardware. We don't have to worry about installing their software. As long as you have a computer with an internet connection and a browser, you can access this program, run these data, and contribute to this fantastic research. My team during this latest school year used this tool to study Theia 303, yet another one of these new structures identified in Gaia. And this one's special because it's home to a K2 planet candidate detected during the Campaign 7. And one of the problems there is that, the K2 mission looked in the ecliptic, and TESS largely avoids the ecliptic. So a lot of the stars in Theia 303 still are lacking light curves. Only 4 of its stars happened to be randomly observed by K2. If we had known about its existence back in 2014 when we were planning the Campaign 7 mission, we would have definitely proposed to look at this. Unfortunately, right now, we don't have that many light curves. But here's what we do know. The first thing is there is some limited RV information for this structure. And my students noticed that along this big stream, or whatever you want to call it, there appears to be 3 unique groupings in radial velocity. So there is some structure along this alleged group. Are these groups related? Are these subgroups related? Are they part of a larger star formation event? Or are they completely unrelated and it's a coincidence that they're in the same place at the same time? Hard to say. but they all appear to be rather young based on the CMDs and what rotation period measurements we were able to complete. But for the northern group, where the planet candidate is, we do have some rotation period measurements from TESS, Kepler, and ZTF, K2 and ZTF. And we also have some lithium abundances from Galah, and they point to a consistent picture that this group is 250 million years old. So we hope that with some more work, we'll be able to validate the planet candidate and pin down the age of this grouping, and we'll be able to add this planet to the small but growing list of young cluster planets. Now, a lot of this work has relied on data that exists for free on the internet in public repositories. This includes the Gaia astrometry, the photometry we use to make the CMDs, the time series imaging from Kepler, TESS, and ZTF that we use to make light curves and measure rotation, and a lot of the spectroscopy from Keck, Lamost, Apogee, and also Galah, and other facilities too. All of this just lives on the internet, and I think that's amazing. It's a big change, and I think it's what it does. It breaks down barriers to entering research. You don't have to have access to a facility. Cutting edge data is at your fingertips, and with tools like I described that my high school team built using this public resource, Google Colab. This is a free resource. People can, with no sophisticated computer required, with no software needing to be installed besides a browser, can access these data and analyze these data and perform research. This is really important for allowing newcomers to enter astrophysics. Finally, I'd like to advertise a fascinating talk by Catherine Minea, who is a graduate student at UT Austin working with Keith Hawkins. I saw this on YouTube during the recent Galah science meeting. And Catherine is using Galah spectroscopy to analyze many of these Theia groups. She's looking at the chemical homogeneity, also the chemical clocks, which encode the birth time. It's like a birth certificate for a star. And also the lithium, which is something that changes over time, the way I now have many gray hairs compared to how I looked 10 years ago. So please check out her talk and that fantastic work. Finally, to summarize, we now see that known clusters have extended diffuse halos and tidal tails, that a lot of the members are actually outside of the tidal radius. And identifying these is really important because we can see how clusters are beginning to dissolve into the galaxy as part of galactic evolution. But it also increases the number of stars around which we can find planets. There's also thousands of new stellar structures identified in Gaia. These might be amorphous blobs, elongated strings or streams, or compact groups. TESS provides a critical resource for confirming that these halos and tails and new structures are actually composed of stars that were born at the same time. There are other facilities, though, that can complement TESS. I like ZTF. Kepler and K2 are obviously amazing facilities. There are lots of other ground-based facilities. This is helpful because TESS does have large pixels. TESS is somewhat limited in brightness compared to Kepler and ZTF. And TESS does have short sectors compared to the ZTF observing season. So this is complementary. Radial velocities. We wish we had lots of radial velocities because that'd make confirming the 3D co-motion very straightforward. There's a lot of ground-based work to do this. Gaia will also continue providing more RVs as time goes on. A lot of these structures are going to be home to transiting planets. Some already known, some waiting to be discovered. And finally, once again, public data and public resources really help bring people into astronomy. Finally, I looked through the posters. Louisa Riebel, Stephanie Douglas, and Lisette Gonzalez have posters on young clusters. And there's talks by Ruth Angus, Luke Bauma, and Mark Popenchak at this conference about stellar rotation and young clusters. So please check that out. Thank you for listening. Bye-bye.